Number 12, back to lengths of pregnancies. The lengths of pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. I can draw that. The normally distributed bell-shaped curve for lengths of pregnancies. Here's the mean of 268 days, and the standard deviation is 15 days. In the A part, we're only concerned with one individual pregnancy. If one pregnant woman is randomly selected, find the probability that her length of pregnancy is less than 260 days. Well, that's definitely to the left of the mean. And since I'm looking for a probability that the pregnancy is shorter than 260 days, would I shade to the left or to the right of 260? To the left, and that means I'm going to use negative 9999 for my left score. That's just 8 days early, a baby being born 8 days before the mean length of a pregnancy. Do you expect that probability to be relatively high or relatively low? Yeah, I don't think it's unusual for a baby to be 8 days early. You don't think twice about that. That's not too much. So I expect to get kind of a high probability here. Do I need to adjust the standard deviation? No, because in Part A, we're just talking about an individual. Let me tell you something, though. What if I just went by the rule, always divide the standard deviation by the sample size? What if I just said always? The standard deviation's 15. In the A part, what's the sample size? 1. What's 15 divided by the square root of 1? It's still 15. So you could always adjust the sample size, but if you divide by 1, it's not going to change. I didn't mean adjust the sample size. I meant adjust the standard deviation. But when you divide by the square root of 1, you're going to get the same standard deviation. So help me figure out what I'm punching on the calculator here. Y'all watch out for me. I often say binomial CDF when I mean normal CDF. If you hear me do that, just point at me and I'll know what I've done, but I don't mean to confuse you. I just misspeak. So you only use binomial CDF when you are dealing with a binomial distribution where there are only 2 possible outcomes. What do I need to have in that argument? From negative 9,999 up to 260, given that the mean length of a pregnancy is 268 and the standard deviation is 15, about 2 weeks. I got that to be about 0.2969. Darn close to a 30% chance. About a third of babies are born a week early, and it's no big deal. But if 25 women are randomly selected and put on a special diet just before they become pregnant, find the probability that their lengths of their pregnancy has a mean less than 260 days. In other words, maybe some guru has come out with a diet, eat only this, this, and this before you get pregnant. and you'll have a lower chance of having a premature baby. Let's say somebody's trying to sell a diet plan, and that's the thing. You eat this while you're trying to get pregnant, and your chance of having a premature baby will be lower. Well, let's see if it is. If the sample size is 25, then I'm still going to enter normal CDF, negative 9999 to 260, given that the mean is 268. But because we're talking about a group of 25 women, and notice the word group may not be in there, but still it's implied you're talking about 25 women instead of one. I have to adjust the standard deviation. It's not just 15, it's 15 divided by the square root of 25. Actually, you could do that in your head pretty quickly. Square root of 25 is 5, and 15 divided by 5 is 3. You could just calculate that in your head and put a 3 right there. Yes, ma'am? Nope, there are 3 possible things for these first 2 numbers. If you have a score and you've shaded forever to the left, you're going to use negative 9999 up to that score. If you have a score and you've shaded to the right, you're going to use that score first. You got to have the left one first, and then positive 9999. Or if the problem says between 2 scores, then you just type in the left one, comma, the right one. All right. I got that to be about 0.0038. About 30% of individual women have pregnancies or have babies a week early. But if we look at groups of 25, the probability that the average length is less than 260 is now down to less than 0.5%. 0.0038 is 0.3% or 0.4%, less than 0.5%. So if the 25 women do have a mean of less than 260 days, does it appear that the diet has an effect on the length of pregnancy? And should medical supervisors be concerned? Let's see. I have to think hard about that. It is, what's the name? The range, not range rule of thumb. I can't think of the name of the theorem that says if you assume one thing and the results or an outcome is highly unusual, but it happens anyway, then what you assumed was probably wrong. Like if you assume a die is fair, then the probability of it landing on 1 is 1/6. But if you roll that die 100 times and 90 of them, it lands on 1, then your assumption that the die was fair is probably not right. The die was probably not fair. So in the B part, we're assuming that the diet is not going to make you have a baby early or late. It doesn't affect the length of pregnancy at all. That's what we're assuming in the B part. In the B part, we found the probability of the pregnancy lasting less than 206 days is about 0.003. Is that unusual? What's our magic cutoff for probability, what we consider usual or unusual? 0.05. That is definitely less than 0.05, or it is unusual for a group of 25 pregnancies to last, to have a mean length of less than 260 days. That's what this probability being less than 0.05 tells us. So the C part is saying if this would be unusual if the diet had no effect on the length of pregnancy, but then it happens, groups of 25 women who had been on the diet all of a sudden were having lengths of pregnancy less than 260 days, what would that tell you? And this is hard to say. You ought to try to teach it. It's rough. If you assume something and then you observe an outcome that's not likely to happen under your assumption, then that means your assumption is wrong. What was our assumption in the B part? That the diet didn't cause you to have a baby early or have a baby late. But if this is highly unlikely and yet it did happen, that's what the C part is saying, 25 women do have a mean of less than 260 days, then our assumption is probably wrong. What does that mean? The diet does have an effect. This diet is causing women to have babies before or more than a week early. Or at least it should make us go, we better check this out some more. Let's see. Does it appear that the diet has an effect on the length of the pregnancy? Yes. How could I make this clear? That's the best way to say it. Something unusual is occurring. It may or may not actually be the diet causing women to have their babies a week early, but it's definitely something that medical supervisors would want to look into. Because if the diet had no effect, then that probably wouldn't happen. If this diet were in some kind of clinical trial, we'd probably just want to do some more sampling and some more testing. All right, I think we have one more. The labeling of M&M packages. Mars says that their M&Ms have a mean weight of 0.8565 grams and a standard deviation of 0.0518 grams. The label of a package containing 465 candies stated that the net weight is 396.9 grams. Actually, on a pack of M&Ms, it'd probably say 400 grams because nobody cares about that other 4.1 gram. Nobody's weighing their M&Ms anyway. But assume that a package had 465 M&Ms and the package said it weighed 396.9 grams. If every package has 465 candies, the mean weight of an M&M would have to be this total weight divided by the number of M&Ms in the bag. Let's just make it easier. If I said there were 400 M&Ms in a bag and they weighed 2 grams each, those would be honker M&Ms, big M&Ms, but I'm just trying to make the math easy. If the bag weighed 400 pounds, had 400 M&Ms, and each M&M weighed 2 grams, then how much would how many? Let me try one more time. If we knew that the bag of M&Ms weighed 400 grams, and we knew that there were 200 M&Ms in the bag, how would we find out how much each M&M weighs? Just divide the total weight by the number of M&Ms in the bag. So that's where this 0.8535 comes from. If you take the weight the bag says divided by the number of M&Ms in the bag, you get the average weight of an M&M. If one M&M is randomly selected, find the probability that it weighs more than 0.8535 grams. Not binomial, normal CDF or inverse norm? Normal CDF because we're looking for a probability. So normal CDF we're looking for the probability that an M&M weighs more than 0.8535. How much more than 0.8535? Forever to the right, an infinitely big M&M that weighed 9,999 grams. There are not going to be any M&Ms out there, so you don't have to worry about it. Given that the mean is 0.8565 and the standard deviation is 0.0518, do I need to make an adjustment on that in the A part? I could divide it by the square root of 1 if I wanted to, but that wouldn't change it. It's still 0.0518. I got that to be about 0.5231. Anybody second that? All right, let me tell you what it means. We're assuming when we buy a pack of M&Ms that Mars is giving us exactly what they told us, that we're getting our money's worth, that the package is labeled correctly. If the package is labeled correctly, then there's still about a 52% chance that I would get an M&M bigger than 0.8535 or heavier than 0.8535. Wouldn't be surprising. I mean, gosh, that's 2 nearest 10,000th of a gram. You're going to have a very precise scale to measure that anyway. But it wouldn't be surprising to get one M&M that was, actually this is underweight. This is 0.0013 grams below average. So what? You get one skinny M&M. But what if we had a whole bag randomly selected and we want the probability that their mean weight is at least 0.8535 grams? .8535 to 9,999. Given that the mean is 0.8565, but I'm not going to use the same 0.0158 for the mean. because I'm not talking about an individual M&M now. I'm talking about 465 M&Ms. So I need to adjust the standard deviation by dividing it by the square root of 465. I got 0.8944. For 1 instead of 4. Oh, okay. All right. I must have just written down that number wrong last time I wrote it. In other words, in not just an individual M&M, but in a whole bag of M&Ms, there's about an 89% chance that the average size of the M&M is as big as it's supposed to be. But an 89% chance that it is as big as it should be means what? What's the complement of that? There's an 11% chance of getting an underweight bag of M&Ms. Now, how much that upsets you just depends on how much you care about getting your money's worth where M&Ms are concerned. If you are an M&M addict, that could upset you. I'm going to say 89% chance that the weight is labeled correctly, but there's an 11% chance of getting an underweight bag of M&Ms. I would be less upset about an underweight bag of M&Ms than a premature baby. So how important, how significant something is just determined by the consequences of what happens next. Remember the difference between statistical significance and practical significance? Would this 11% chance of getting an underweight bag of M&Ms make you want to sue Mars, the Mars Candy Company? Probably not. But what if some prenatal vitamin was causing 11% of pregnant women to have premature babies? That would be a lot and probably would have practical significance. It would probably be